but this is a very cool one. Uri's going to be talking about intro to vector search. He's okay.
Okay, first of all, thank you all for coming. And this is going to be a pretty introductory talk to vector search and why do we actually need some fancy things like Milvus and other vector search engines, and why can we just iterate and do matrix multiplication. So hopefully by the end of this talk, you know the capabilities of vector search and vector stores. So let's get started. This is our agenda for today. A few words about me, about Argmax. Then we'll talk about recommendation systems. We're a search and recommendation consulting firm, so we care a lot about recommendation systems. Then we'll talk about approximation algorithms. And this is the main reason why you probably need a vector search, or at least you should care about vector search if you do anything at scale. Then we'll talk about similarity search architectures in general. And then we'll talk about what I think is the new standard for vector search and database. So let's get started. This is me, my two sons and dog. Actually, we now have 2 dogs. I'm one of the organizers of PyData NYC, also a pretty cool meetup. I have a podcast in Hebrew. If you didn't catch my accent, I'm originally from Israel. One of the, it's not that hard, but one of the most popular podcasts in Hebrew on machine learning. I used to work for Microsoft, AT&T, Yahoo. Then I founded a machine learning startup for analyzing legal documents that was acquired by a company here in New York in 2020. And then I started Argmax, a consulting firm. So this is me and my history. Argmax caters for 2.5 sectors. Our 2 main sectors are EdTech, advertising technologies, companies like F-Flyer, Sport Illustrated, etc. And we have quite a few insurance companies and financial services companies. And a rising star is companies developing tools for creator economy. If you might have heard about companies like Artlist, Lightricks that develop tools for content creators. Cool. So who here never heard about a recommendation system or doesn't know what it is? Who here designed a recommendation system? Cool, so only one? So 2. That slide is a bit pretentious, but essentially a recommendation system is any use case where you have a lot of items. You can think about products, ads, resumes if you're looking for a job, and you have a lot of users, but you have limited space. So you need to make a decision which items are you going to show to which users, and you need to be kind of conservative about that. So most recommendation systems are essentially a ranking problem, and sometimes you can kind of play with that, like what is at the top, what's at the bottom, what is after a click. But that's like a pretty bird's eye view on recommendation systems. In theory, we can think about it like having some huge imaginary matrix of all of the possible users and all of the possible items. And if we're able to predict in advance, would John here in the yellow circle, would he buy a jar of cookies? Yes or no? That's in theory what we want to do. And we don't actually do that. We actually try to segment users and sometimes to represent items by their features and not by their IDs. And we try to predict what is the likelihood of John or people like John to buy cookies or any other sort of carb. That's the theory. Now that we have these probabilities that we're trying to predict, if we're able to vectorize the cookie jar into a vector, all of the items into vectors, and all of the users into vectors, such that their multiplication would be approximately that big matrix, then essentially we're in the gold. And why is that? Because we can use those same vectors for 2 use cases. The first is to have user-to-item recommendation. This is like the Spotify For You page or something like that. But we can also have the product page recommendation. When you, for example, when you visit the product page for cookies, you can see, I don't know, ice cream and other things, other sweets, because their vector is similar to the cookie vector. So one solution, one vector presentation can essentially cater for two use cases. Now, how do we actually do that? So unfortunately, I don't have the answers. There are a lot of courses on recommendation systems. A lot of people did a master's degree on various ways how to actually vectorize items and users. There are roughly two extremes. One of them is to do content filtering or content representation, trying to understand the content really well. For example, if John is vegan and the product is vegan, and in this representation, we can actually assign a value for each feature or each property, then we can recommend vegan items to vegan users. It could be keto or any other property that you can name. This is content filtering. The other extreme, also known as collaborative filtering, is not caring about the items at all and about the users at all, saving them, regarding all of them as IDs, and just trying to recommend similar items to similar users. For example, if a certain user buys both keto items and, I don't know, sports magazines, they doesn't have to share the same features. They just co-occur. So that's the other extreme. In reality, we kind of mix and match. So it really depends on the use case. Cool. So let's assume that we have this crazy magic encoder that encodes an item. And we can also train another encoder that would vectorize a query. We have the same architecture for just simple search, right? Now we can vectorize with a lot of models like OpenAI and other embedding models, BGE, Splade, that Tim mentioned before. But in theory, once you have this black box of an encoder, this is how a search looks like. Pretty simple. And what about personalized search? Almost the same, right? We just add the user vector, we concatenate them, and there you go. You have a personalized search architecture. It sounds pretty simple because it is. No, just kidding. There are a lot of details that needs to fall into place. But the bottom line is that we have a lot of vectors, right? And someone needs to manage them and actually make them to put to good use. Okay, so let's start with the basic question. There you go. This is an implementation, a full implementation. It's actually working of a vector search. So what's the problem with this implementation? Why do we actually need Milvus and other fancy tools if this pretty naive implementation works? Any ideas? So the answer was essentially the complexity. And this is true. So let's try and think about vector search at scale. So this is kind of a back of the envelope calculation. Let's assume that we have M users and N items, and the dimensionality of the embedded vector is D. Then we have a lot of operation, M and D square. Plus, we actually need to sort the items, right? So we have an additional K log K complexity, which as N and M goes to infinity and you have a lot of items and a lot of users, is very costly. So this is why the naive approach is not always the best solution. So on the other hand, if you can do the naive approach, do that, right? If you have 1,000 items and even 1 million users, you'll be just fine. That's something that you can run on your local PC without too much effort. Now, another advantage of using the naive approach is that you can be pretty creative with the distance metric. Most of the distance metrics that you'll see in models these days are like inner product, cosine similarity. You won't see anything fancy like a Levenstein distance or anything like that because it's hard to optimize. But if you're doing the naive approach, sure, do whatever. But as mentioned, the problem is scale. And let's talk about our first heuristic. I'm going to start with hierarchical search because this is the most commonly used heuristic. By the way, also used in Milvus. It's also known as the HNSW. I think it stands for hierarchical nearest small world something. But sorry? What he said. But what's important is the H, is the hierarchy. So what's the main idea here? So let's assume that I'm searching for John, and I'm looking for John K nearest neighbors. That's our premise. Now, if I know something about John, I don't need to search the entire world, right? I can start by searching his zip code, right? Looking for, I don't know, 1,000 neighbors. And if unfortunately his zip code only has 2 neighbors, I can go one level up and look in his state. If I didn't find enough neighbors in his state, I can look in his country, and so on and so on. So assuming that I have a hierarchy, it really helps speed things up, and I don't need to look in all of my possible candidates. Why is that an approximation? Well, can this strategy actually go wrong? Great answer. So this strategy doesn't work if John is actually like on the border of 2 states, for example, right? Because then you're going to find a lot of neighbors that share his zip code, but are not actually the closest neighbors. So that's an approximation algorithm. It's the most popular one. It's pretty scalable, and it's the de facto standard in most vector searches these days. Another alternative, commonly used in sparse vectors. For example, algorithms like Splade that Tim mentioned before use variants of inverted indices. One known algorithm is the IVF. I'm not going to try to elaborate on the initials this time. And the idea is as follows. If I know that the majority of the entries of the vector are zeros, I only need to look up the non-zero indices in order to estimate the inner product. Right, so you can think about a huge vector, for example, the size of the vocabulary, 300,000 words, that has only 3 non-zero values. I can search only for other vectors that have other non-zero entries in that specific indices. It's very efficient, right? Because I don't search the entire globe like the previous example. I only search a small subset. But it's approximate. For example, if I have a vector with a lot of non-zero entries with close to 0 values that might have sum up to a huge value, then I'm going to miss out. So this approach is pretty useful in search engines like Lucene, Elasticsearch, in which we use the bag of words representation. And the last approach, which is probably the fastest one, but also the least accurate, relies on hashing. But not only hashing, this is the locality-sensitive hashing. We're trying to hash values in some manner that preserves some of their proximity. Not all of it. For example, let's take this pretty simple approach. Let's assume that this is John's vector, right? I can hash it only to keep the sign of the vector, right? Minus, plus, plus, and then look for neighbors in the same quartile. So it's not the same, right? It's not super accurate. It has some sort of distance aspect to it. It's super fast because hashing is super fast. but it's the least accurate. So this is kind of our last resort. For example, if we have a lot of hardware constraints, this is probably the best use case, but it has also the lowest recall. There are definitely other approaches, but these are the three main branches of approximate vector search. And let's try to summarize what are the trade-offs. So obviously, if you can do a flat naive search, it's the best approach. It doesn't really scale. And the most efficient one is the LSH, but it's also not as accurate as you'd like. The de facto standard for dense vectors these days is HNSW. And IVF is probably the standard for sparse vectors. So that's roughly sums it up. So now we know how a vector search is actually built, but how do we use it to build something that actually provides value? So this is how recommendation systems looks like. Let's assume that I have a user. I know how to encode it. And I already indexed all of the items in my vector search. This is a pretty simple search or recommendation flow. In most cases, we also would like to incorporate partitions. For example, if John here really likes bagels, but John is currently traveling in France and there aren't any bagels in the stores, it doesn't really help me, right? So I want to recommend the item, the most similar available item, right? So you can think about it conceptually as having several vector searches, vector stores for each partition. This is not necessarily how things are actually implemented, but conceptually, it's a good way to think about the problem. And this pre-filtering is pretty helpful when I know in advance what I'm going to filter on. Sometimes I don't. For example, what if the product is no longer available, out of stock or recall or anything that I can't really recommend it and show it to the user? This process is called a post-filtering because I cannot know beforehand what item is going to be available or not. One pretty common technique is just to, if I need 10 items, to query for 15 and hope for the best. There are some more sophisticated search engines that can kind of incorporate some of the filtering logic into the query. Vector searches like Vespa. I'm not sure if Milvus can do that. And Milvus, obviously. And this is the post-filtering part of a recommendation system. And there are quite a few vector stores. And I'm pretty sure this doesn't really cover even 50% of the available vector stores these days. We are a consulting firm. We do not have any preference, but obviously Milvus is the best, right? Now, regarding which one is the best and features and all of that, I would just let you decide for yourself. There is this pretty cool website, and I'm pretty sure that since I took this screenshot, a lot of things changed. This is embedding-based. Here you can see how each open source vector store scales. There's also another website called the big-benchmark.com for vector stores of size billion and more, if I recall. But it really depends. If scale is what you're looking for, benchmarks.com is pretty helpful. There are also other considerations that you might want to think. And I try to list some of them in this very not so approachable slide. What data are we indexing? Is it dense or is it sparse? Some vector stores handle dense data better. Some are kind of hard-coded to sparse data. Do we need to update the vectors after we index them? Delete or modify? Some vectors searches support them, some do not. For example, the HNSW algorithm has some problem with modifying vectors after indexed. Do we need to support, do we use the GPU or not? Do we want to run it on an edge device or not? So a lot of considerations that you need to take into account. And I think that the most important one is, are we running the queries one by one or in batch mode? So again, pretty important. Which brings us to like the most inconvenient question for team. Is vector search a product on its own or just a feature in Postgres or Redis or another database? So Tim, what do you say?
It's clearly a product because of the amount of things you need now to be in production.
Cool.
The level of features, backup, restore, security, encryption, different type of searches, different type of indexes. All those things are a lot to expect from someone who builds a completely separate data.
So you all heard Tim, it's definitely a feature. And this is how we regard the vector stores. We try to be as agnostic as possible to the vector store. And there are a lot of libraries like the Vexim API. And this is a library that we developed. There's also a similar library by Redis. A pretty unknown library, LangChain, maybe you heard about them, also have an abstraction to the vector store. And I think that this is a good way to go. From our perspectives, some of our clients use Mongo, some of them use Postgres, some of them use Redis, some of them use some cloud provider offering. And if you want to be agnostic and not to be in a vendor lock-in, you probably want a level of abstraction above your vector search. And there are quite a few. Also Chroma that I didn't mention here. Cool. So it was a pretty long talk. So this is the gist. Think about vector similarity as a new standard. And like databases where you have a connection string and you're pretty agnostic to database, use some sort of an abstraction layer so you won't be, so you will be agnostic to the vector search. There's a trade-off between performance and accuracy. We've seen that across the three approximation algorithms, HNSW, LSH, the flat, and the HNSW. And think about your use case. Not all use cases require very high scalable data. Some of them are simpler to manage. That's it. I hope you had fun and learned something.